In this lesson for Chapter 8, we're going to set out to find ways to prove or justify things that we might know intuitively. We've talked about words like growth and decay, especially when they come to exponential functions, exponential growth, exponential decay, and visually you can tell certain functions are steeper than others, but we're going to talk about how to formalize that, okay, how to actually prove it and justify it rather than just saying, well, I looked at it and this function looks like it's steeper than another function, okay? And I apologize for my stuffiness. My head is all stuffed up this morning. L'Hopital is going to be helpful in how we justify this today as well. We use words like growing faster or growing slower to describe functions that are more or less steep than another. And we do that by formatting a ratio. So if we want to compare two functions, f and g, we're going to take the ratio of the two. Put one in the numerator and one in the denominator. And then investigate the limit as the limit approaches infinity. So as the limit approaches infinity, what's the result? If the result is also infinity, then f grows faster than g. In other words, the numerator is growing at a rate faster than the denominator if the limit result is infinity. If the limit result is 0, so when we approach infinity, if the limit result is 0, then the denominator is going to be the faster one or the steeper function. So depending on where the steeper function is, you'll get a different limit result. If the numerator is larger, your result will be infinity. If the denominator is larger in its growth rate, the result will be 0. And if you get any other numerical value that's neither 0 nor infinity, some other limit value, okay, not 0 and not infinity, then we say that they grow at the same rate. We're not saying that they are the same function, but that they're growing at the same rate, which would essentially mean that they are parallel and that the gap between them is not growing at all. They're just growing at the same rate, heading straight up at an equivalent rate to the other one. Okay, so show that an exponential function grows faster than a cubic. So logically, you could picture, we know that exponential functions really shoot up fast and they have a very steep rate of increase. But if we want to prove it, we're going to investigate what happens when we take the limit of the ratio of those two. So going to infinity, we want to compare e to the x over x cubed. And our initial result would be e to the infinity over infinity cubed, which is infinity over infinity. So that's inconclusive because it's indeterminate. So we'd want to back up and put L'Hopital to work for us here. So of course the numerator would still be e to the x, and we get 3x squared, which is still infinity over infinity. So we'll use L'Hopital one more time, and that'll give us e to the x over 6x, which is still indeterminate. And one more time we'll do L'Hopital. My numerator is still e to the x, my denominator is 6. Now we'll get e to the infinity over 6, which is infinity, not indeterminate. So we can conclude that the numerator function, that e to the x, grows faster than x cubed. So again, it's intuitive. It should make sense to you, but we're formalizing it and how to prove it with limits. Show that ln of x grows slower than x. In other words, that x grows faster. So we want to tackle that as a ratio as well. Now you can do x over ln x, or you could do the ln x on the top. Either way, the result should end up showing you that x has the faster growth rate and that ln x does not. So, it doesn't matter to you. To me, just show me your work either way. So let's show this one. All right, because that's infinity over infinity, it's indeterminate. We'll have to apply our derivatives. So the derivative is 1, and then 1 over x. And simplifying that, we get x, which means we get infinity. And if we get infinity, then that means that the numerator grows faster than ln of x. Or you could do it the other way, okay, if you happened to pick that one. Okay, that is also indeterminate. So then we can take our derivatives, which would be 1 over x over 1. In other words, 1 over x, or 1 over infinity, which is equal to 0. When you get 0 as a result, then that means that the numerator is the slower one. So ln of x grows more slowly than x, which is the same. It's saying the same thing. Show that they grow at the same rate. So we're talking about the function x over x plus sine of x, or the function, or the limit, x plus sine of x over x. Now either will work, but one is going to be easier to do than the other, and it's actually the second one is going to be easier to do. So we're going to focus on that one instead. This would be infinity plus the sine of infinity, which oscillates between 1 and -1 over infinity. So that is indeterminate. So we want to use either algebra or use L'Hopital. Basic algebra helps me out if I just use common denominators. So I'll get x over x plus sine of x over x. That's going to give me 1 plus the sine of x over x. And sine of x over x is one of those limits that we learned way back in chapter 1 of AB calculus. And so that's 1 plus the value of 0, which is 1. And that's not equal to either. It's not equal to 0, and it's not equal to infinity. And so that means those two things grow at the same growth rate. They are essentially parallel to each other, meaning they're growing in steepness as they essentially parallel. Okay, I'm not saying they're exactly parallel, but it's as if they are growing at generally the same rate. Even graphically, you could think about that. X is a line that grows up oblique like that. So it has a steady growth rate. X plus sine of x doesn't have a steady growth rate, but it grows generally. It's a little faster and a little slower, but on average, it's growing at a similar growth rate. So it's enough similar that we say that they grow at the same growth rate. Growth rates are transitive. Okay, the word transitivity means if a property applies to two of them, 2 out of the 3, and then another property applies to a different 2 out of the 3, that the property would apply to all 3 of them. So in calculus, we would say if f grows at the same rate as g, and g grows at the same rate as h, then by the transitivity property, then f must grow at the same rate as h. So it's just a connecting all three things by the one that they have in common. So here we can say that f and h are related to each other by the same growth rate because they're both related to g. So here's three different functions. We have an f function, which is defined as a square root. We have a g function defined as the square of a square root, and then we're given a third function, which is straight out h of x equals x, and show that f and g are growing at the same rate. Well, why wouldn't we just not use h at all? Why would we not just show that the limit approaching infinity? Why wouldn't we just take f by itself and g by itself and then just work that out? Why do we have to involve h of x at all? Well, the challenge is that the algebra here is complex. I'm not saying it's not doable, but it's more work than I care to do. So let's find out a relationship between the others first, and that'll be it'll accomplish the same thing in a simpler way. So let's take the limits of f of x and let's compare it to h of x rather than g of x. So we're going to take x squared plus 4 and compare it to x. Now that's infinity over infinity, so you can use L'Hopital. You can also use algebra to simplify that. It's kind of your choice, one or the other. If you want to do L'Hopital, that's fine. Just don't forget about the chain rule and make sure you're careful about all of that. Otherwise, we can use algebraic simplification methods. Maybe I'll do one of each. I'll do algebra right now. So my algebra says that I can replace x in the denominator with the square root of x squared. Those two, they are equivalent. The square root of x squared is the same thing as x, but now I have two square roots, so that algebraically I can combine them to 1. So I could have the square root of x squared plus 4 over x squared in the same square root, which would allow me to simplify that because they have a common denominator. And so I can simplify that to 1 plus 4 over x squared. And then when I substitute in infinity, and I get a denominator of infinity, that'll give me the square root of 1 plus 0, or 1. And because I got a constant, the implication is that those two things grow at the same growth rate. So let's try the other limit. Let's look at the limit of g of x compared to h of x. So the limit would be quantity 2 rad x minus 1 squared over x as well. Now I tried this with L'Hopital and then I tried it algebraically, and the algebraic way ended up to be easier, so that's what I'm going to show you right now. It's similar to what we did the other time, but we're going to modify the denominator. X is the same in this case as rad x quantity squared. So I'm manipulating this time so that I use parentheses like the numerator has parentheses, whereas last time I used a square root as the main thing because the numerator had a square root. So I can consolidate these into one quantity, and I can say, okay, it's 2 rad x minus 1 over rad x, and the whole quantity is squared, which allows me to do a little bit more algebra with common denominators. So it'll be 2 minus 1 over the square root of x, quantity squared. Then I could put infinity into that. There's 1 over the square root of infinity, which is 0. So that'll give me 2 squared, which is 4, which is a constant again. And the constant means the two things are growing at the same growth rate. So we've shown that functions f and g grow at the same growth rate as function h, so they must grow at the same rate as each other as well. The last thing we want to talk about is a mnemonic device, a memory trick, to help you remember which functions have faster growth rates than others. It's a silly nonsense word called NFEPL, and each of those letters stands for a type or a category of function. The N, the double N there, we call this a super exponential. It's a type of function that has the base that has a variable and the power that has a variable. So maybe x to the sine of x. So the base is varying and the power is varying. Another example might be x plus 2 to the ln of x. So the base has a variable, power has a variable. It might be, excuse me, it might be the square root of x to the x minus 4 power. It would not be e to the x. That would not count in this category because the base doesn't have an x in it. So I call those super exponentials. These grow faster than any other function. They related to any other category, they are going to be the steepest. They're going to have the most rapid growth rate. F stands for a factorial function. A factorial function is a function that involves an exclamation point. So that's not very commonly used. We are going to use it quite a bit in chapter 9, but it's not super common outside of when we're going to do sequences and things like that. So a factorial is a function that grows by multiplication, where you multiply all of the numbers up to that point. So for example, if I said something like 5 factorial, that is 5 multiplied by 4 and 3 and 2 and 1. And so then what is the result of that? And that works out to be 120. So a factorial function at every position takes it's a multiplication of all of those. So those also grow very steeply compared to most other functions, but not quite as steeply as the super exponential category. We have E, which stands for all other exponential functions. So that would cover the e to the x, it would cover 3 to the x, it would cover 10 to the x minus 2, any function where the base is constant and the variable is in the power. P stands for polynomials. Polynomial is going to be x to the second, x to the fifth, any of these where the base is a variable, but the power is a constant. So that includes, x to the rad 7. That would be a constant as well. It even does include plain x, because that, of course, just has a constant power of 1. And the last is L, and that stands for all logarithms. And all logarithms of any kind are the most slowly growing function. So that includes common logs, it includes natural logs, it includes logs of any other base. So NFEPL, it's most helpful on a multiple choice question where you don't have to prove it. So everything we've done up to this point, we've been proving it with limits. If you're looking at a question that's multiple choice, this little ordering technique where you don't have to show any work just allows you to order things fairly quickly. So our last slide is just to put these in categorical order from fastest growing to slow growing. And so you want to check, do I have any of the n to the n? And so that would be that exponent, the x to the exponent. So that would come first. Then we have any factorials, and there aren't any in that question. Then we have any exponentials, and we do have 3 different exponentials in this one. Our exponentials, 2 to the x is an exponential, e to the x is an exponential, but so is the natural log of 2 to the x. That is also an exponential function because the natural log of 2 is a constant, just like 2 and just like e. So how do you put those in order? Which one would you put first? Well, you want to compare the relative values of 2 and e and the natural log of 2. So we know that e, or you should know, the value of e is larger than 2. It's 2 point, it's a irrational number, but it's 2 point something, so it's larger than 2. The natural log of 2 is a decimal value that's smaller than 2. So if we're going to put these in order, e to the x would come first because its decimal value is larger than 2. 2 to the x would come next, and then the natural log of 2 as a quantity to the x power would come fourth, I guess. Then we get to p for polynomial, so x squared is last, and then L would be if we had any logarithms. So a lot of times people might be tempted to put this last. They just are quick, they're hustling, they see logarithms, so they put it at the end. But it's not actually a logarithm. It is logarithm of 2, which is a constant number raised to a power. So be careful as you watch that. Again, best used for a multiple choice question. It's not a legitimate a reason or a justification on a free response. You would never use it on a free response to prove it, but you can use it on a multiple choice. All right, thanks for your attention. I hope you have a good rest of your day, and I look forward to seeing you tomorrow.